Somewhere in our galaxy right now, a dead star 12 miles wide is bending reality itself. Its magnetic field is so powerful that it tears apart empty space. One burst from this cosmic monster released more energy in 1/10 of a second than our star will produce in 100,000 years. This is not a black hole. This is something that might be even stranger. A magnetar. An object so extreme that it breaks the rules of physics we thought were unbreakable. If you enjoy uncovering the universe's darkest secrets, hit that like button and subscribe, because what we're about to explore will change how you see the night sky. Prepare yourselves. We begin. A massive star reaches the end of its life. It has burned for millions of years, fusing elements in its core, building heavier and heavier atoms. Then the fuel runs out. In less than a second, the core collapses. The outer layers rebound in a supernova explosion that outshines entire galaxies. Everyone knows this story. But here's what they don't tell you. Not every stellar corpse becomes a black hole. When the star is just heavy enough, between 8 and 20 times the mass of our star, something different happens. The core doesn't collapse completely into a singularity. Instead, it stops. It crushes down to a sphere just 12 to 15 miles across, but it doesn't vanish into a black hole. What remains is a neutron star, a city-sized ball of matter so dense that a teaspoon of it would weigh as much as Mount Everest. But some neutron stars are born with a twist, literally. When the core collapses, it spins faster and faster, like an ice skater pulling in their arms. The magnetic field that existed in the original star gets compressed too. Squeezed into that tiny space, the magnetic field intensifies to levels that should not be possible. The result is a magnetar. This is confirmed science, not theory. We've detected these objects, we've measured their emissions, and the numbers are terrifying. A magnetar's magnetic field reaches strengths of 10 to the 15th Gauss. That's 1 quadrillion times stronger than Earth's magnetic field. It's 1,000 times more powerful than a typical neutron star. At that strength, the magnetic field itself becomes dangerous. Picture this. If a magnetar existed halfway between Earth and the Moon, roughly 120,000 miles away, it would erase every piece of magnetic data on the planet. Credit cards, hard drives, everything. But that's the least of our problems. The real danger is what that field does to matter itself. Because here's where physics starts breaking. At distances closer than 600 miles from a magnetar, the magnetic field becomes so intense that it warps the shape of atoms. Electrons, which normally orbit in spheres, get stretched into thin needles. Atoms stop behaving like atoms. The very building blocks of chemistry cease to function normally. And this is just the beginning. What happens when you get even closer? Imagine crushing our star down to the size of a city. Not Hollywood's version of crushing, real physics crushing. Every atom smashed so tight that there's no space left between them. That's what you're dealing with. A magnetar is roughly 12 miles in diameter. You could drive across it in 15 minutes. Yet packed into that impossibly small sphere is 1.4 times the mass of our entire star. This isn't an estimate. Scientists have measured magnetar masses through their gravitational effects on nearby objects and the frequency of their pulses. The numbers are consistent and deeply disturbing. How does this work? In normal matter, atoms are mostly empty space. The nucleus sits in the center, electrons orbit far away, and between them is nothing. But when a star collapses into a neutron star, gravity crushes everything together. The electrons get forced into the nucleus, combining with protons to form neutrons. What remains is neutrons packed shoulder to shoulder, with no gaps. This creates matter at nuclear density. That means 1 cubic inch of magnetar material would weigh over 600 million tons. A sugar cube of this stuff would weigh more than all of humanity combined. If you somehow dropped a teaspoon of it onto Earth, it would slice through the ground like it wasn't there, punching straight through to the other side of the planet. The density is so extreme that the surface gravity becomes nightmarish. Stand on a magnetar, and you'd experience gravity 200 billion times stronger than Earth's. That's 2 times 10 to the 11th. You wouldn't just be crushed. Your atoms would be ripped apart and smeared across the surface in a layer 1 atom thick. But even this isn't the strangest part. Because magnetars don't just sit still. Their surfaces move, they crack, they quake. And when that happens, the entire universe notices. The magnetic field holds the magnetar's crust in place, like a vice. But the crust itself is crystalline iron, harder than diamond, floating on a sea of superfluid neutrons. As the magnetar spins and its magnetic field shifts, stress builds up in this crust. Eventually, something has to give. What comes next makes earthquakes look gentle. On December 27, 2004, something hit Earth. Not physically, but every satellite in orbit detected it. Radio telescopes around the world went haywire. The ionosphere, 60 miles above us, was suddenly illuminated. Scientists scrambled to figure out what happened. The source was 50,000 light-years away. A magnetar designated SGR 1800-6-20, and it had cracked. This wasn't a small event. When a magnetar's crust fractures, it releases energy that makes our most powerful weapons look like firecrackers. The December 27 event released more energy in 1/10 of a second than our star produces in 150,000 years. From 50,000 light-years away, it was brighter than a full moon to our satellites. This is confirmed data from NASA and multiple observatories. Think about that distance, light traveling for 50,000 years, and the burst still arrived strong enough to affect our planet's atmosphere. If this magnetar had been just 10 light-years away, the same distance as some of our nearest stars, the radiation would have stripped away Earth's ozone layer. Complex life would have ended. But what actually happens during a starquake? The magnetar's iron crust, under immense magnetic stress, suddenly shifts. It might move less than a millimeter. That's it, a fraction of an inch. But when you're moving crystalline iron harder than diamond, packed at nuclear density, even a millimeter displacement releases unimaginable energy. The magnetic field lines snap and reconnect violently, like rubber bands stretched to their limit and released all at once. This magnetic reconnection accelerates particles to nearly the speed of light. Gamma rays and X-rays spray out in all directions. The magnetar rings like a bell, its vibrations creating pulses we can detect across the galaxy. These starquakes can continue for weeks. The magnetar sends out aftershocks, each one releasing more energy than our star produces in years. The surface settles into a new configuration, slightly different from before. The magnetic field geometry shifts, and then it might stay quiet for years or decades. Or it might crack again tomorrow. We can't predict it. Each magnetar behaves differently. Some are active, erupting multiple times per year. Others go silent for decades before suddenly awakening. We're still trying to understand the pattern. Because the real mystery is what powers all of this. Where does a magnetar get the energy to keep doing this? You can't see a magnetar's field, but it's there, always. A sphere of twisted magnetic energy surrounding the dead star, reaching out hundreds of miles in every direction. And this field doesn't just attract metal, it destroys reality. At 600 miles from a magnetar, the magnetic field strength hits about 1 billion Gauss. That's confirmed through spectroscopic measurements of magnetar atmospheres and the cyclotron resonance features in their X-ray spectra. At this distance, quantum mechanics starts failing. Here's what that means. Normally, light travels in straight lines through empty space, but near a magnetar, light bends. Not because of gravity this way, but because of magnetism. The magnetic field is so strong that it affects the vacuum itself, something called vacuum birefringence. Photons traveling through this space split into two beams based on their polarization, Space itself becomes birefringent, like looking through a crystal. But it gets worse for anything with matter. Remember, atoms are held together by electromagnetic forces. Electrons orbit nuclei because of electric attraction, but a magnetar's magnetic field is strong enough to overwhelm these forces. The field doesn't just tug on electrons, it deforms them. At distances inside 600 miles, atoms elongate into needle shapes. The electron clouds that should be spherical get stretched along the magnetic field lines. Chemical bonds stop working the way they should. Molecules can't form properly. Complex chemistry becomes impossible. For any living thing, this is instant death. Not from heat, not from radiation, though there's plenty of that, but from the fundamental breakdown of molecular structure. Your cells would stop functioning before you even felt pain. The proteins that run your body would unfold. DNA would unravel. You'd come apart at the molecular level. Nothing we've built could survive this either. Spacecraft hulls would have their atomic bonds disrupted. Electronics would fail instantly as the magnetic field induces currents millions of times stronger than they're designed to handle. Even light itself struggles to escape, bending and splitting as it fights through the distorted space. And this is all assuming you could somehow survive the radiation, which you couldn't. Because magnetars don't just sit quietly in their magnetic cocoons. They scream. The field isn't static. It shifts, twists, and reconnects constantly, even between major starquakes. Each reconnection event sends out bursts of X-rays and gamma rays. These aren't gentle pulses. They're focused beams of high-energy radiation powerful enough to ionize anything in their path. But compared to what the field does to space itself, even this seems almost normal. Light is supposed to be simple, photons traveling in straight lines, unaffected by magnetic fields. That's what we learned. That's what works everywhere else in the universe. But near a magnetar, this rule breaks down completely. Scientists first predicted this in the 1930s, but they thought it would never matter. The effect, called photon splitting and vacuum birefringence, only becomes significant in magnetic fields approaching 10 to the 13th Gauss or higher. No natural object should reach that strength. Then we found magnetars. Here's what happens. In normal space, a vacuum is truly empty, but quantum mechanics tells us that's not quite true. Even in a perfect vacuum, virtual particles constantly pop in and out of existence. Electron-positron pairs appear for impossibly brief moments, then annihilate each other. We can't see this happening, but it's real. It's been measured in laboratories through the Casimir effect. Near a magnetar, the magnetic field is so strong that it polarizes this quantum vacuum. The virtual particles align with the field before they disappear. This alignment changes how light travels through space. The vacuum effectively becomes a medium, like air or glass, but made of quantum fluctuations. Light passing through splits into two beams with different polarizations. One beam polarized parallel to the magnetic field, another perpendicular to it. They travel at slightly different speeds. This is vacuum birefringence, and we've confirmed it through observations of magnetar spectra. The light arriving from these objects shows exactly the polarization patterns this theory predicts. But there's another effect, even stranger. At even higher field strengths, above 10 to the 13th Gauss, individual photons can split. A single high-energy gamma-ray photon can spontaneously divide into 2 or 3 lower-energy photons. This isn't science fiction. This is quantum electrodynamics pushed to its absolute limit. We've observed this indirectly. When magnetars have major flares, the spectrum of radiation we detect doesn't match what we'd expect from a simple hot surface. There are features, dips, and peaks in the spectrum that only make sense if photon splitting is occurring. The high-energy gamma rays are splitting into lower-energy X-rays before they reach us. This means that magnetars are natural laboratories for testing quantum mechanics in conditions we can never recreate on Earth. Our most powerful magnets reach maybe 45 Tesla, about 450,000 Gauss. A Magnetar's field is roughly 2 billion times stronger. It's testing physics in a regime we can only dream of accessing artificially. And yet, this isn't even the most extreme thing Magnetars do, because sometimes they don't just bend light, they weaponize it. March 5th, 1979. Every satellite orbiting Earth picked up something impossible. A wave of gamma rays and X-rays slammed into our planet's atmosphere with such intensity that it ionized the upper layers. Scientists initially thought it was a nuclear attack. The burst lasted for only 1/5 of a second, but in that instant, it delivered more energy than our star produces in 1,000 years. The source was a magnetar in the constellation Norma, about 30,000 light-years away. Designated SGR 0505-66. What we witnessed was a massive magnetic flare, the largest ever recorded. This is fully documented. The data came from Soviet Venera spacecraft, American satellites, and observatories worldwide. The event was so powerful that it remains the brightest burst of energy ever detected from beyond our solar system. But here's what makes it truly terrifying. That energy traveled for 30,000 years through empty space. It spread out over an expanding sphere. By the time it reached Earth, it had diluted across an area trillions of miles wide, and it still hit us hard enough to disrupt satellites and alter our ionosphere. Calculate backwards, and the numbers become nightmarish. At the moment of the burst, the Magnetar released roughly 10 to the 46 joules of energy. That's more energy than an entire galaxy of 200 billion stars produces in several years. From a single object 12 miles across, in 1/5 of a second. How is this even possible? The leading theory involves catastrophic magnetic field reorganization. The Magnetar's magnetic field, already at impossible strengths, became unstable. Magnetic field lines twisted and tangled over years or decades until they couldn't sustain the configuration anymore. Then they snapped. Imagine rubber bands wrapped around a ball, twisted tighter and tighter. Eventually, they break and whip back violently. But these aren't rubber bands. These are magnetic field lines carrying energy equivalent to the mass of small moons, according to Einstein's equation linking mass and energy. When they reconnect, all that energy has to go somewhere. It goes into accelerating particles. Electrons and ions get flung outward at 99% of light speed. These particles slam into the Magnetar's own magnetic field further out, creating cascades of gamma rays through a process called synchrotron radiation. The Magnetar effectively creates a massive gamma ray cannon, firing in all directions. For months after the March 1979 event, astronomers detected a pulsing X-ray source at the same location. The Magnetar was still vibrating from the violence of the flare, sending out regular pulses every 8 seconds as it rotated. Even after the catastrophic release, it still had enough energy to outshine thousands of normal stars. And this raises a disturbing question. If Magnetars can do this once, can they do it again? Can they do it bigger? Nobody was looking for Magnetars. The word didn't even exist yet. Scientists in the 1970s were still wrapping their heads around neutron stars and pulsars, those rapidly spinning stellar remnants that sent out regular radio pulses. Then, on March 5th, 1979, the universe decided to introduce us to something far more violent. The gamma ray burst that hit Earth that day didn't fit any existing model. It was too bright, too brief, and too energetic. It came from a fixed point in the sky, not from a distant galaxy. And in the months after, that same spot kept pulsing with X-rays every 8 seconds. This wasn't a pulsar behaving normally. This was something else entirely. Scientists called it a soft gamma repeater, or SGR. The name described what they saw but not what it was. It repeated, unlike most gamma ray bursts. And the spectrum was softer, meaning lower energy than typical gamma ray bursts from cosmological distances. But what could cause such behavior? Robert Duncan and Christopher Thompson proposed the answer in 1992. They calculated that a neutron star with a magnetic field powerful enough could store enormous energy in its twisted magnetic field lines. When those field lines snapped and reconnected, they would release bursts of gamma rays and X-rays. They called these objects magnetars, combining magnetic and star. The theory was controversial at first. Some scientists argued that magnetic fields couldn't reach such extreme strengths. Others questioned whether the field could remain stable. But observations kept piling up. More SGRs were found. Their behaviors matched Magnetar predictions. And in 1998, researchers finally measured a magnetic field strength directly. They did this by observing cyclotron resonance features in the X-ray spectrum of a magnetar. When charged particles spiral in a magnetic field, they emit radiation at specific frequencies determined by the field strength. By measuring these frequencies in the X-ray light coming from magnetars, scientists calculated fields of 10 to the 14th to 10 to the 15th Gauss, exactly what Duncan and Thompson had predicted. Since then, we've identified about 30 confirmed magnetars in our galaxy and nearby galaxies. There are probably more we haven't found yet, either because they're dormant or hidden behind dust. Each one we study reveals new mysteries. Some are hyperactive, bursting multiple times per year. Others stay silent for decades. Some emit radio waves. Others don't. We're still learning the rules. But the discovery taught us something profound. The universe can create objects more extreme than we imagined. And if magnetars exist, pushing magnetic fields to their theoretical limits, what else might be out there, pushing other forces to their breaking points? August 27, 1998. The Rossi X-ray Timing Explorer satellite was doing routine observations of the sky when something extraordinary happened. A magnetar designated SGR 1900+14 erupted in a massive flare. The burst was so intense that it saturated the satellite's detectors, overwhelming them with more X-rays than they were designed to handle. For several hours, the telescope was effectively blind. Its instruments had to reset and recalibrate. Engineers on the ground worried about permanent damage. This wasn't a design flaw. The satellite was built to study X-ray sources. But nobody anticipated an object that could suddenly become 100,000 times brighter in less than a second. This event wasn't unique. Multiple X-ray satellites over the years have been temporarily disabled by magnetar flares. In 2004, when SGR 1800-6-20 had its giant flare, it affected over a dozen spacecraft. Swift, Integral, RHESI, and others all recorded the burst. Some instruments went into protective modes. Others had their data corrupted by the sheer intensity of the radiation. Think about what this means. These satellites orbit Earth, about 93 million miles from our star. They're designed to observe X-ray sources billions of light years away. They have filters, shielding, and safety protocols to handle intense radiation. Yet a magnetar tens of thousands of light years away can still overwhelm them. The implications are staggering. If a magnetar flare can blind a satellite across interstellar distances, what would it do up close? The answer is nothing survives. Any spacecraft within several light years of a major magnetar flare would be fried instantly. The radiation would induce currents in every circuit, melting electronics. Solar panels would degrade from the bombardment. Shielding would be useless against such intensity. But here's the really concerning part. We have no warning system. Magnetars don't announce when they're about to erupt. There's no precursor we can detect. One moment they're relatively quiet, sending out steady X-ray emission. The next moment, they explode with energy equivalent to thousands of supernovas compressed into fractions of a second. For future space exploration, this is a hidden danger. As we send probes deeper into our galaxy, they might encounter magnetars we haven't catalogued yet. A probe could be cruising through interstellar space, completely unaware that a dormant magnetar lies a few light-years away. Then, without warning, that magnetar wakes up. The probe would die before its sensors even registered what happened. Scientists are now working on better detection methods. They want to map every magnetar in our galaxy and monitor them constantly. Early warning could save missions. But there's a problem. Dormant magnetars are almost invisible. They emit so little radiation that we can barely detect them. We might have dozens or hundreds lurking in our galaxy, completely unknown, and each one is a loaded weapon, waiting to fire. Our galaxy contains roughly 200 billion stars. About 1 billion of those will eventually explode as supernovas. Many will leave behind neutron stars. Scientists estimate there might be 100 million neutron stars scattered throughout the Milky Way. Yet we've only confirmed about 30 magnetars. What makes them so rare? The answer starts with how they're born. Not every neutron star becomes a magnetar. The original star needs specific conditions. It must be massive enough to produce a neutron star, but not so massive that it collapses into a black hole. That's a narrow range, roughly 8 to 20 times our star's mass. But mass alone isn't enough. The star also needs to be spinning rapidly when it collapses. As the core compresses, conservation of angular momentum makes it spin faster. This spinning, combined with the convective motions in the collapsing material, creates a dynamo effect. This dynamo amplifies the magnetic field to extreme levels. Think of it like a cosmic generator. The collapse itself generates the initial energy. The spinning motion organizes that energy into a coherent magnetic field. But this only works if conditions are just right. The rotation speed, the mass distribution, the initial magnetic field strength, all these factors have to align. It's rare. Even when a magnetar forms, it doesn't stay that way forever. The extreme magnetic field gradually decays over time. Scientists estimate that magnetars remain active for only about 10,000 years, maybe less. After that, the field weakens to normal neutron star levels. The object settles down, becoming an ordinary pulsar or simply a quiet neutron star. This short, active lifetime explains why we see so few. At any given moment, only a small fraction of neutron stars are in their magnetar phase. The rest have either not yet become magnetars or have already passed through that phase. It's a brief, violent stage in a neutron star's long existence. But there's another reason our count stays low: detection. Magnetars are small, about 12 miles across. They're incredibly distant, often tens of thousands of light-years away. And unless they're actively flaring, they're dim. Many might be dormant right now, invisible to our telescopes, waiting for their next outburst. We only find magnetars when they do something dramatic. A major flare lights them up across the electromagnetic spectrum. Then we can study them, measure their properties, confirm they're magnetars. But a quiet magnetar could be lurking nearby, and we'd never know. In fact, scientists suspect there might be many more magnetars than we've confirmed, perhaps hundreds in our galaxy alone. Most are dormant, their surfaces cooling, their magnetic fields slowly decaying. They'll flare again eventually, years, decades, or centuries from now. But until then, they remain hidden, which means there might be one closer than we think. Distance usually means safety in space. A supernova 10,000 light-years away is spectacular but harmless. Even a gamma-ray burst, if it's not pointed directly at us, poses no threat from such distances. But magnetars change the calculation completely. Scientists have run the numbers, and they're disturbing. If a magnetar within 10 light-years of Earth experienced a giant flare, one comparable to the December 2004 event, the radiation would be devastating. The burst would hit our atmosphere with enough energy to destroy the ozone layer partially. UV radiation from our star would spike. Extinction events would follow. But here's what keeps astronomers up at night. 10 light-years is close, very close. There are only about a dozen stars within that radius. The odds of a magnetar being that close are extremely low. But 10,000 light-years? There are millions of stars at that distance, and we know magnetars exist in that range. We've detected them. A hyperflare from 10,000 light-years away wouldn't destroy our ozone, but it would cause noticeable effects. The ionosphere would light up, satellites would be damaged, radio communications could fail, and if the flare was strong enough, if it reached the extreme end of what magnetars are theoretically capable of, even from that distance, it might cause biological harm. The worst-case scenario involves a magnetar hyperflare pointed directly at Earth. Remember, magnetars emit focused beams of radiation from their magnetic poles. As they rotate, these beams sweep across space like lighthouse beams. If Earth happened to be in the path during a giant flare, we'd receive the full intensity, not just scattered radiation. From 10,000 light-years, such a beam could deliver radiation doses comparable to being near a nuclear explosion. Not everywhere on Earth, just the side facing the magnetar at that moment. But that would be enough. Power grids would fail from the electromagnetic pulse, electronics would fry, and living tissue would absorb dangerous levels of gamma rays and X-rays. Scientists estimate that a magnetar hyperflare from this distance could increase cancer rates worldwide for decades afterward. It wouldn't be an immediate extinction event, but it would be a catastrophe. And there's no way to prepare, no warning system, no defense. The geological record might already contain evidence of past magnetar flares. Some mass extinctions have no clear cause. Researchers have looked for signs of increased radiation exposure in the fossil record. Certain layers show mutations and cellular damage consistent with radiation exposure, but the source remains unknown. Could a magnetar have fired at Earth millions of years ago? We can't prove it yet, but the possibility exists, and it's chilling. Because somewhere out there, right now, a magnetar might be building up stress in its crust. In years or decades, it will crack. Its magnetic field will unleash a beam of death into the galaxy, and all we can do is hope we're not in the way. Imagine standing on a magnetar's surface. You can't, because you'd be dead, but imagine it anyway. Under your feet, if you had feet, is a landscape that defies everything we know about solid matter. The crust is iron, pure iron, compressed to densities millions of times greater than steel. It's arranged in a crystalline structure so perfect that it makes diamonds look disordered. This is the hardest substance in the universe. Nothing we can create comes close. Laboratories have tried to simulate these conditions and failed. The pressures and densities are simply beyond our reach. But this iron isn't static. The intense magnetic field threads through it, creating currents and eddies of electric charge. These currents generate heat, not the kind of heat you feel from a fire. We're talking millions of degrees. The surface temperature of a young magnetar can reach 10 million degrees. That's hotter than the core of our star. At these temperatures, even crystalline iron starts to behave strangely. The outer layers, just the top few yards, exist in a state between solid and liquid. The atoms vibrate so violently that they can slip past each other, like a metal that's almost melting but held in place by the crushing gravity. Deeper down, the pressure increases and the material stays solid, but the surface has this weird plasticity. When a starquake happens, this iron crust cracks, but not like glass shattering. The crack moves at a significant fraction of light speed, propagating through the ultra-dense material faster than sound in normal matter. The two sides of the crack suddenly shift, creating a shear motion that releases the stored magnetic energy. The surface ripples. Waves move through the solid iron like water ripples in a pond, except these ripples are moving through material billions of times denser than water. The magnetar rings like a bell, oscillating at specific frequencies determined by its size, mass, and internal structure. These oscillations continue for weeks or months, gradually damping down as the energy dissipates. But the surface doesn't just crack and ring, it also erupts. The magnetic energy release heats material to billions of degrees in microseconds. Iron vaporizes despite the intense gravity trying to hold it down. A plume of ionized iron plasma, an atmosphere suddenly created by violence, rises above the surface. This atmosphere is temporary, lasting maybe seconds or minutes before gravity pulls it back down. During those brief moments, the Magnetar has a real atmosphere, thin but detectable. Spectroscopic observations have actually captured this. When Magnetars flare, their spectra show absorption lines from iron, silicon, and other elements. These lines tell us what the surface is made of and how hot it is. The data confirms our models. The surface is indeed iron, and it's indeed unimaginably hot. Beneath the crust lies something even stranger, a liquid layer of neutrons, unbound from protons, flowing freely. Scientists call this a neutron superfluid because it flows without any friction or viscosity. Deeper still, the neutrons might form exotic states of matter that we can barely describe with current physics. But all of that is hidden beneath the iron, and the iron itself is already beyond our comprehension. Most magnetars don't have atmospheres, not like Earth's atmosphere, anyway. The gravity is so intense that any gas would be pulled down and crushed into the surface almost instantly. But magnetars do have something, a layer so thin it's barely there, yet so heavy it defies belief. Scientists call it a photosphere, though that's not quite accurate. It's the region where photons can finally escape from the dense material below. In normal stars, the photosphere is thousands of miles thick. In a magnetar, it's measured in centimeters, sometimes less, a layer just 1 atom thick. But that layer weighs millions of tons per square inch. The density is so high that a single cubic centimeter contains more mass than a mountain. The photons struggling to escape through this layer get scattered billions of times, bouncing between atoms and electrons before finally breaking free. This scattering alters the spectrum we observe, creating the unique fingerprints that identify magnetars. The magnetic field plays a crucial role here too. It's so strong that it confines any material trying to escape. Electrons, ions, everything gets trapped along magnetic field lines. They can move along these lines, but not across them. The result is a highly structured atmosphere, more like columns and sheets than a uniform gas layer. When a magnetar flares, the magnetic field lines above the surface reconnect. This magnetic reconnection suddenly releases trapped material. Plasma that was held in magnetic loops gets flung outward at high speeds. For a brief time, the magnetar develops a real atmosphere, extending maybe 100 miles above the surface. This ejected material cools as it expands, emitting X-rays and gamma rays. We can observe this emission with our telescopes. The spectrum shows features that reveal the temperature, density, and magnetic field strength of the material. It's one of the few ways we can probe conditions near a magnetar's surface. But gravity always wins. The escaped material doesn't have enough velocity to reach escape velocity. It arcs back down, crashing into the surface at speeds of thousands of miles per second. The impact creates more X-rays, more heat, and sometimes triggers additional magnetic activity. The whole event can last hours or days. Between flares, the atmosphere essentially disappears. Individual atoms might hover temporarily before falling back. Particles trapped in magnetic field lines spiral endlessly, but there's no continuous gaseous layer, no weather, no atmospheric circulation, just crushing gravity, searing radiation, and magnetic field lines so twisted they form cages of force. This is as close to a naked stellar core as nature allows. The surface of a magnetar is matter at its limit, physics at its breaking point, and yet, somehow, it's stable. It exists. A 12-mile sphere of impossibility, floating in the dark, waiting to remind us that the universe still has secrets we can't explain. Einstein taught us that gravity warps space-time. The stronger the gravity, the more time slows down relative to an outside observer. We've tested this with atomic clocks on airplanes and satellites. The effect is real, but near a magnetar, time doesn't just slow down, it nearly stops. Calculate the gravitational time dilation at a magnetar's surface, and you get numbers that seem wrong. For every second that passes on the magnetar, roughly 1.3 seconds pass for someone far away. That's a 30% difference. If you somehow stood on a magnetar for 1 year, about 16 months would pass for the rest of the universe. This isn't speculation. The math is straightforward general relativity. We can measure it indirectly through the light coming from magnetars. Photons climbing out of the intense gravitational field lose energy. They get redshifted, their wavelengths stretched. The amount of redshift tells us exactly how strong the gravity is, and the calculations match theoretical predictions perfectly. But time dilation creates strange situations. Imagine watching a magnetar from a distance with a perfect telescope. You see its surface. A starquake happens. From your perspective, the crack spreads across the surface more slowly than it would if you were right there. The oscillations that follow appear stretched out in time. The entire event looks like it's happening in slow motion. Meanwhile, if you were somehow on the surface, time would feel normal to you. The crack would spread at its true speed. The oscillations would ring at their natural frequency. You wouldn't notice anything strange about time itself. It's only when you compare your clock to a distant observer's clock that the difference appears. This has real consequences for the physics happening on the magnetar. Nuclear reactions, particle decays, all processes that depend on time, run at different rates depending on where you measure them. A neutron near the surface would decay more slowly from an outside perspective than a neutron far from the magnetar. The difference is measurable. Scientists use these time dilation effects to test general relativity in extreme conditions. Magnetars provide a natural laboratory where gravity is strong enough to create noticeable effects, but not so strong that it collapses into a black hole. They're right at the edge, the perfect testing ground. Some researchers have proposed that magnetars could be used for precision tests of alternative gravity theories. If general relativity breaks down anywhere, it would be here, where space-time is stretched to its limit. So far, the observations match Einstein's predictions. But we keep watching, keep measuring, hoping to find a crack in the theory. Because if general relativity does fail near magnetars, it would revolutionize physics. We'd need new theories to explain what holds these objects together, how they behave, why they don't collapse. The implications would ripple through every branch of science. But for now, Einstein still reigns. Time bends near magnetars, exactly as he predicted. And that bending is yet another way these objects warp reality itself. Here's a problem that keeps physicists awake. Magnetic fields decay. Always. Every magnet you've ever held will eventually lose its magnetism. The atoms that create the field slowly drift out of alignment. Energy dissipates as heat. It's inevitable. So why don't magnetar fields decay? They do decay, actually, but incredibly slowly. Scientists estimate a magnetar's field has a half-life of about 10,000 years. That means after 10,000 years, the field strength drops by half. After another 10,000, it halves again. Given enough time, a magnetar should become an ordinary neutron star with a much weaker field. But here's the mystery. The energy stored in a magnetar's magnetic field is enormous. We're talking about 10 to the 47 joules, roughly the mass energy equivalent of a small planet, according to Einstein's famous equation. That energy has to come from somewhere, and it has to be maintained somehow, at least for a while. The leading theory involves the magnetar's rotation. When a magnetar forms, it's spinning incredibly fast, maybe 1,000 times per second. This rotation, combined with convective motions in the newly formed neutron star, could generate the initial magnetic field through a dynamo process. It's similar to how Earth generates its magnetic field, but cranked up to impossible extremes. But there's a catch. For this to work, the magnetar needs a power source to drive the dynamo. Rotation provides some energy, but not enough. Scientists think the key might be in the magnetar's internal structure. Neutron stars aren't uniform spheres. They have layers, crusts, superfluid cores. Different layers might rotate at different speeds, creating shear forces. These forces could maintain the magnetic field. Another possibility involves exotic matter. In the core of a neutron star, pressures are so extreme that neutrons might break down into their constituent quarks. These quarks could form strange states of matter, like quark-gluon plasma or even stranger configurations. Some theories suggest that these exotic states have unique magnetic properties that could sustain ultra-strong fields. We don't know which theory is correct. Maybe all of them contribute. Maybe there's another mechanism we haven't thought of. The data we have isn't detailed enough to rule out options. We need more observations, better models, and perhaps new physics to fully understand how magnetars maintain their fields. But here's what we do know. The field is there. It's measured, it's confirmed, and it's doing things that shouldn't be possible according to our standard models of magnetic field decay. Magnetars are violating expectations, pushing beyond what we thought nature allowed. And every observation raises new questions. Some magnetars seem to have fields that are increasing rather than decreasing. How is that possible? Others show complex field geometries that don't match simple models. The field isn't just strong, it's structured, twisted, knotted in ways we're only beginning to map. These objects are telling us that we don't understand magnetic fields as well as we thought. Not at extreme energies, not in extreme conditions. And until we crack this mystery, magnetars will remain one step ahead of our theories. Not all magnetars behave the same way. Some are hyperactive, erupting dozens of times per year. Others go silent for decades, only to suddenly wake up with a massive flare. This inconsistency has puzzled scientists since we first discovered these objects. What determines a magnetar's behavior? SGR 1800 6-20 was dormant for over 20 years, quiet, unassuming. Then, on December 27, 2004, it produced the largest burst ever recorded. The entire astronomical community was stunned. What triggered it? Why then? We still don't have complete answers. Compare that to SGR 1900+14, one of the most active magnetars known. Between 1998 and 2002, it erupted hundreds of times. Some bursts were small, others were major events. Then it calmed down. Now it's relatively quiet, only producing occasional bursts. What changed? Scientists have proposed several theories. One involves the magnetar's age. Young magnetars, recently formed, might be more active because their crusts are still settling. The magnetic field is still reorganizing, causing frequent starquakes and flares. As the magnetar ages, it stabilizes and activity decreases. This matches some observations, but not all. Another theory focuses on the magnetic field geometry. If the field is highly twisted and complex, it might store more energy and lead to more frequent reconnection events. Simpler field geometries might be more stable, but we can't directly observe a magnetar's field structure. We have to infer it from the timing and spectrum of bursts, which leaves a lot of uncertainty. Temperature might also play a role. Magnetars cool over time as they radiate away their internal heat. A hotter magnetar might have a more fluid interior, allowing the crust and core to interact more dynamically. This could trigger more starquakes. As the magnetar cools, the interior stiffens and activity drops. This theory has some support from thermal emission observations, but none of these theories fully explain the data. Some magnetars don't follow the expected patterns. They stay active longer than they should, or they go quiet earlier than predicted. And the sudden awakening of dormant magnetars, like the 2004 event, suggests that even a seemingly dead magnetar can harbor hidden stresses ready to erupt. There might also be external factors we haven't considered. Could interactions with nearby objects trigger flares? If a magnetar is in a binary system, maybe the companion star's gravitational influence causes tidal stresses that eventually lead to starquakes. Most known magnetars appear to be isolated, but we might have missed companions in some cases. Or perhaps it's purely random. The stresses build up chaotically, and when the crust finally cracks, depends on countless tiny factors we can't measure or predict. Like earthquakes on Earth, magnetar flares might be fundamentally unpredictable beyond statistical probabilities. This unpredictability is both fascinating and frustrating. It means every magnetar is a unique case study. It also means we can't forecast when the next major flare will happen. All we can do is watch, wait, and hope our telescopes are pointed in the right direction when it occurs. Gamma-ray bursts are the brightest events in the universe. For a few seconds, a gamma-ray burst can outshine every other object in the observable cosmos combined. Astronomers have detected these bursts from galaxies billions of light-years away, so distant that the light has traveled for most of the universe's history, and magnetars might be creating some of them. Most gamma-ray bursts come from two sources we've identified. Long-duration bursts, lasting more than 2 seconds, come from massive stars collapsing into black holes. Short-duration bursts, under 2 seconds, come from neutron-star collisions. But there's a third category. Some bursts don't fit either model. They're too short to be collapsing stars, too bright to be ordinary neutron-star mergers. And their spectra show features that match magnetar flares. In 2004, when SGR 1800-6-20 had its giant flare, it was briefly visible from the Andromeda galaxy, 2.5 million light-years away. If that same event had occurred in a distant galaxy, say 10 billion light-years away, we would have detected it as a short gamma-ray burst. We might have classified it as a neutron-star merger or some other event, never guessing it was actually a magnetar. This realization changed how we interpret gamma-ray bursts. Some bursts we've been attributing to other causes might actually be magnetar giant flares. If true, it means magnetars are even more common than we thought. Every galaxy might host dozens or hundreds of these objects, occasionally producing bursts we can detect across cosmic distances. But there's an even more intriguing connection. Some scientists think magnetars might power certain types of supernovas, not the supernova that creates the magnetar, but later events. Here's how it could work. A young magnetar, spinning incredibly fast, could inject energy into the expanding debris of its parent supernova. This energy would make the supernova appear much brighter and last much longer than normal. We've observed supernovas that don't match standard models. They're too bright or they fade too slowly. Researchers call these superluminous supernovas. Some have spectra consistent with magnetar-powered emission. The magnetars spin down energy as it gradually slows due to magnetic braking, gets converted into radiation that lights up the surrounding gas. It's like having a cosmic light bulb inside the supernova remnant. If this is correct, magnetars aren't just interesting in their own right. They're key players in multiple cosmic phenomena. They shape supernova evolution. They create gamma-ray bursts. They might even seed the universe with heavy elements through their violent eruptions. The material they blast into space, enriched with iron and other metals, could contribute to the chemical makeup of future generations of stars and planets. This web of connections shows how important magnetars are to cosmic ecology. They're not isolated oddities. They're part of the grand cycle of stellar birth, life, and death. And every time we study one, we learn something new about how the universe works. Imagine this scenario: a massive star, roughly 200 light-years from our solar system, reaches the end of its life. It explodes in a supernova. We see the light show, beautiful, harmless at that distance. But the core collapses into a magnetar. What happens next? Initially, nothing. 200 light-years is far enough that even a magnetar poses no immediate threat. Its magnetic field, while intense, drops off rapidly with distance. At 200 light-years, the field strength would be negligible. We wouldn't detect anything unusual beyond the supernova itself. But magnetars don't stay quiet. Within years or decades, it would have its first major flare. Let's say it produces a burst comparable to the December 2004 event. The radiation would travel toward Earth at light speed. 200 years later, it would arrive. The burst would light up our night sky, not as bright as the full moon, but noticeable. A point of light suddenly appearing, brighter than any star. It would last less than a second, then fade. Astronomers would scramble to figure out what they just witnessed. Telescopes would focus on the location, and they would find the magnetar, still pulsing, still sending out X-rays. But here's the concerning part. The radiation dose Earth receives from 200 light-years would be minor. Background levels would spike slightly. Satellites might experience minor glitches, but nothing catastrophic. Now imagine the magnetar is only 20 light-years away. At 20 light-years, a giant flare would be dangerous. The X-ray and gamma-ray dose would penetrate our atmosphere significantly. The ozone layer would take damage. Not complete destruction, but enough to increase surface UV radiation for years. Cancer rates would climb. Ecosystems sensitive to UV would struggle. Marine plankton, which form the base of the ocean food chain, would die off in large numbers. At 10 light-years, we're in catastrophe territory. A magnetar giant flare from this distance would be an extinction-level event. The ozone layer would be shredded. UV radiation from our star would sterilize the surface. Complex life would retreat to caves and deep oceans. Some species would survive, but most wouldn't. Human civilization would face collapse. And here's the truly terrifying thought. We wouldn't know until it was over. The flare travels at light speed. There's no warning. One moment, everything is normal. The next, our sky lights up with deadly radiation. By the time we detect it, we're already bathed in it. There's no time to prepare, no chance to protect ourselves. Fortunately, the odds are extremely low. Massive stars capable of producing magnetars are rare. Most are far away. The nearest known massive star is probably over 100 light-years away. And even if it did go supernova, the chance of the core becoming a magnetar, rather than a black hole or regular neutron star, is maybe 1 in 10. And then the chance of it flaring toward Earth during its brief active lifetime is even smaller. But the universe is old and large. Somewhere, sometime, a civilization might not be so lucky. They might live near a magnetar, and when it wakes up, their story ends. Black holes get all the attention. They're the universe's ultimate destroyers, the objects that swallow everything. Nothing escapes, not even light. Pop culture loves them. Movies feature them as cosmic villains. But ask a physicist which object is actually more dangerous, and you might get a surprising answer: magnetars. Here's the argument. Black holes destroy through gravity. Get too close, past the event horizon, and you're gone. But the event horizon is small. For a stellar mass black hole, maybe 60 miles across, stay outside that radius, and you're relatively safe. Yes, there's radiation from the accretion disk if the black hole is feeding, but a dormant black hole, one not actively consuming matter, is essentially invisible and harmless unless you fly directly into it. Magnetars kill at a distance. Their magnetic fields extend thousands of miles. Their radiation bursts travel across light years. They don't need to be close to cause damage. A magnetar could be sitting 10 light years away, and if it flares in your direction, you're dead. A black hole 10 light years away is just another dark object in space. The destructive range is completely different. Scientists have calculated the danger zones. For a black hole, the lethal radius is measured in thousands of miles at most. You have to be practically touching it for gravity to tear you apart. For a magnetar, The lethal radius extends to potentially dozens of light years. When accounting for giant flares, that's billions of times larger. But black hole advocates push back. They argue that black holes are forever. A magnetar is active for maybe 10,000 years. A black hole exists until the universe ends. Given enough time, a black hole will consume more matter, destroy more structure, and have a greater cumulative impact on the universe. They also point to supermassive black holes at galaxy centers. These monsters contain billions of times the mass of our star. When they're actively feeding, they create jets of radiation and matter that extend hundreds of thousands of light years. These jets sterilize entire regions of galaxies, preventing star formation and wiping out any life that might have emerged. No magnetar can compete with that scale of destruction. Yet the magnetar supporters have a counter-argument. Those supermassive black holes cause gradual destruction over millions of years. A magnetar flare is instant, civilization ending in less than a second. There's something uniquely terrifying about that immediacy. Black holes give you time, magnetars don't. There's also the question of which is more violent relative to size. A magnetar 12 miles across can release more energy in a fraction of a second than thousands of stars produce in years. A stellar mass black hole, even when feeding actively, can't match that energy output. Pound for pound, magnetars win. The debate remains unresolved. Both objects represent physics at its most extreme. Both can end worlds, but they do it differently. Black holes erase through gravity, slowly, inevitably. Magnetars attack with radiation and magnetism, suddenly, explosively. Maybe the real answer is that we should fear both. The universe has created multiple ways to destroy life, and arguing about which is worse seems pointless when either one near Earth would mean the end of everything we know. Every atom in your body except hydrogen came from stars. This isn't poetry, it's confirmed science. Carbon, oxygen, nitrogen, iron, all these elements were forged in stellar cores and scattered into space when stars died. But there's a mystery. Some heavy elements, the really massive ones, shouldn't exist in the quantities we observe. Creating elements heavier than iron requires specific conditions. You need intense neutron bombardment, temperatures in the billions of degrees, and precise timing. Supernovas provide some of this. Neutron star collisions provide more. But calculations show these sources alone can't explain all the heavy elements we detect in the universe. Something else must be contributing. Enter magnetars. When a magnetar erupts, it doesn't just release radiation, it ejects matter. Neutron-rich material from the surface gets blasted into space at significant fractions of light speed. This material is incredibly dense, packed with neutrons that haven't yet decayed, and it's moving through a radiation field intense enough to drive nuclear reactions. These conditions are perfect for rapid neutron capture, the R process that creates heavy elements. Neutrons slam into existing nuclei, building heavier and heavier atoms in milliseconds. Gold, platinum, uranium, elements that are rare and precious on Earth, form in abundance during these violent events. The magnetar is essentially a cosmic foundry, manufacturing heavy elements through pure violence. Scientists have found evidence supporting this in meteorite samples. Some ancient meteorites contain isotope ratios that don't match supernova predictions. They show excess amounts of certain heavy elements, enriched beyond what standard models produce. The ratios match what you'd expect from R-process nucleosynthesis in extreme magnetic fields. The implications are staggering. Every gold atom in existence might have passed through a magnetar flare billions of years ago. The platinum in catalytic converters, the uranium in nuclear reactors, the rare earth elements in electronics, all possibly created during moments of unimaginable violence on magnetar surfaces. But there's more. The ejected material doesn't just float off into space, it slams into the surrounding gas and dust at high velocity, creating shock waves. These shock waves compress the material, triggering star formation. New stars, born from Magnetar ejecta, would be enriched with heavy elements from the start. Their planets would have more metal, more complex chemistry, better conditions for life. This creates a feedback loop. Magnetars create heavy elements. Those elements form new stars and planets. Some of those stars eventually become magnetars themselves. The cycle continues, gradually enriching the universe with heavier and heavier elements. Over billions of years, this process transforms the chemical composition of entire galaxies. We might owe our existence to magnetars, Earth's iron core, the metals in our technology, even the trace elements essential for biology, might have originated in magnetar flares billions of years ago. Without these violent events, our planet might have been too metal poor to develop complex life. So the next time you hold a piece of gold or use a device with rare earth elements, remember, that matter survived the most extreme conditions in the universe. It was born in magnetic fields that warp reality, ejected in flares that outshine galaxies, and scattered across space to eventually become part of your world. The universe creates through destruction, and magnetars are its most efficient creators. In 2007, astronomers detected something completely unexpected, a brief radio pulse, lasting just 5 milliseconds, coming from billions of light years away. The burst contained as much energy as our star produces in an entire day, compressed into a time span shorter than a heartbeat. They called it a fast radio burst, and nobody knew what caused it. At first, scientists thought it was an error, radio interference from Earth-based sources, satellite glitches, anything but an actual cosmic signal. But more bursts appeared. Different telescopes, different locations, all detecting similar pulses. By 2020, astronomers had catalogued over 1,000 fast radio bursts. They were real, they were common, and they were mysterious. Here's what made them strange. The bursts came from random directions across the sky. They didn't repeat, at least most of them didn't. They showed no pattern. The energy required to produce them was enormous, yet the source had to be incredibly small to pulse that quickly. Only a compact object could flicker in milliseconds. That meant neutron stars or black holes. But doing what? Some fast radio bursts did repeat. The same spot in the sky would pulse again days or months later. This was crucial. It meant the source wasn't destroying itself. Whatever created these bursts survived to burst again. That ruled out catastrophic events like supernova explosions or neutron star collisions. Then, in 2020, came the breakthrough. A fast radio burst was detected from within our own galaxy. The location matched a known magnetar, SGR 1935 plus 2154. The timing matched a period when the magnetar was actively flaring. The connection was undeniable. At least some fast radio bursts come from magnetars. But how? Magnetars emit X-rays and gamma rays during flares. Radio waves are completely different, much lower energy. Creating intense radio emission requires specific conditions. Charged particles need to be accelerated in magnetic fields, then made to emit coherent radiation. It's a complex process that scientists are still working to understand. The leading theory involves magnetic field line reconnection outside the magnetar. When field lines snap and reconfigure, they create electric fields that accelerate electrons to extreme speeds. These electrons, moving through the intense magnetic field, emit synchrotron radiation. Under the right conditions, this radiation becomes coherent, amplifying into a powerful radio pulse that beams out into space. Not all scientists accept this explanation. Some argue that magnetars can't produce the brightest fast radio bursts we've detected. Those require even more extreme conditions. They propose alternatives involving binary systems, strange quark matter, or even more exotic physics. The debate continues. What we do know is that fast radio bursts are now a tool for studying the universe. The radio waves travel through intergalactic space, getting dispersed by free electrons along the way. By measuring this dispersion, we can calculate how much matter the signal passed through. This tells us about the distribution of material between galaxies, the stuff we normally can't see. Fast radio bursts have also revealed that the universe is more crowded than we thought. If magnetars are producing these signals, and we're detecting thousands of them from distant galaxies, then magnetars must be incredibly common. Every galaxy might host hundreds or thousands. We're only seeing the tip of a vast population, and here's the unsettling part. Some fast radio bursts are coming from objects billions of light years away. The signals left those sources when the universe was young. We're detecting echoes of magnetar violence from cosmic dawn. And if magnetars existed back then, they might have shaped the early universe in ways we're only beginning to understand. Inside every magnetar is a mystery. We know the outer crust is crystalline iron. We know there's a neutron superfluid layer beneath. But the core, the very center where pressure reaches its absolute maximum, that's where things get strange. And some physicists think the core might contain matter that doesn't exist anywhere else in the universe. At the center of a magnetar, the pressure reaches 1 to 2 times 10 to the 35 pascals. That's a number so large it's meaningless in everyday terms. It's billions of times higher than the pressure at Earth's core. At these extremes, neutrons themselves might break down into their constituent quarks. This creates quark matter, a state so dense that the boundaries between individual particles blur. Quarks normally exist in groups of 3, forming protons and neutrons. But under extreme pressure, these groups might dissolve. The quarks would flow freely, creating a quark-gluon plasma similar to what existed microseconds after the Big Bang. Laboratory experiments at particle colliders have created tiny amounts of this material, existing for mere moments. Inside magnetars, it could be stable and permanent. But there's an even stranger possibility: strange quark matter. Quarks come in 6 types, called flavors. Up and down quarks form normal matter. But there are also strange quarks, charm quarks, top and bottom quarks. Under normal conditions, these exotic quarks are unstable and decay quickly. But at magnetar core pressures, strange quarks might become stable. If this happens, the core could transform into strange quark matter, a material theorized but never confirmed. This substance would be denser than normal neutron matter and potentially more stable. Some calculations suggest that strange quark matter might actually be the true ground state of matter, meaning regular atoms are just metastable configurations waiting to convert. This leads to a terrifying scenario. If strange quark matter is more stable, contact with normal matter could trigger a chain reaction. The normal matter converts to strange matter on contact. This conversion releases energy, triggering more conversions. In theory, a single speck of strange matter could convert an entire planet in minutes. Scientists call these hypothetical objects strange stars or quark stars. From the outside, they'd look similar to neutron stars. Same size, similar mass, similar surface gravity. But the interior would be fundamentally different. And some researchers think magnetars might actually be quark stars rather than neutron stars. The extreme magnetic fields could be a signature of the exotic matter inside. There's limited evidence supporting this. Some magnetar observations show properties that don't quite match pure neutron star models. Their masses, radii, and cooling rates sometimes deviate slightly from predictions. These deviations could indicate an exotic composition, but the data isn't conclusive. Regular neutron stars with unusual internal structure might also explain the observations. Testing this requires better measurements. We need to precisely determine magnetar masses and radii. We need to observe their cooling behavior over decades. And we need to detect their gravitational waves, if they produce any. These measurements could reveal whether the cores are made of neutrons or something stranger. The implications extend beyond magnetars. If quark matter exists stably in nature, it changes our understanding of matter itself. It means the periodic table isn't the end of the story. There are denser, more compact arrangements of quarks waiting to be discovered. And somewhere in the universe, in the cores of the densest objects we know, that matter exists right now. We might be living in a universe where most matter is in an excited state, kept from its true form only by the absence of extreme pressure. Magnetar cores could be windows into the fundamental nature of reality, showing us what matter really is when gravity strips away all pretense. February 18th, 2008, the European Space Agency's Integral satellite was conducting a routine gamma-ray survey. Its instruments were calibrated, its systems nominal. Then, without warning, every detector went blind. The satellite's data stream filled with noise. Engineers on the ground scrambled to understand what happened. The culprit was SGR 0508-66, a magnetar about 16,000 light-years away. It had erupted in a massive flare, sending a wave of gamma rays and X-rays across the galaxy. The burst lasted only seconds, but in that time it delivered more high-energy radiation to Integral than the satellite normally received in months. Integral wasn't designed for this. Its instruments could handle typical gamma-ray sources, even powerful ones. But a magnetar flare at close range, cosmically speaking, overwhelmed every safety margin. The detectors saturated. Electronics experienced massive induced currents from the electromagnetic pulse. For several minutes, the satellite was effectively useless. But here's the remarkable part. Integral survived. Its systems rebooted automatically. Detectors reset themselves. Within an hour, the satellite was back online, slightly damaged but functional. It had been hit by radiation equivalent to a point-blank nuclear explosion, and it kept working. That's engineering excellence combined with incredible luck. The luck was in the orientation. When the burst arrived, Integral happened to be positioned so its main instruments were pointing away from the magnetar. The radiation hit the side of the spacecraft, not the sensitive detector faces. If the satellite had been oriented differently, the instruments would have taken the full blast directly. They probably wouldn't have survived. Other spacecraft weren't so fortunate. The Swift satellite, designed specifically to detect gamma-ray bursts, was also observing when the flare hit. Its instruments saturated even more completely than Integral's. It took hours to fully recover. Some detectors showed permanent damage, slightly degraded performance that persisted for the rest of the mission. The Mars Odyssey orbiter, circling Mars at the time, detected the burst as well. It wasn't even designed to observe gamma rays, but the flare was so intense that its radiation sensors, meant to measure particle flux near Mars, went off scale. For a moment, Mars Odyssey thought it was being bombarded by a solar storm. Only later did scientists realize the radiation came from across the galaxy. This event taught spacecraft designers a hard lesson. The universe contains hazards they hadn't fully accounted for. Magnetar flares are rare, but they're catastrophic when they occur. Future deep space missions need shielding and protection against sudden radiation surges that might come from any direction without warning. NASA and other space agencies now factor magnetar flares into their risk assessments. For missions to the outer solar system, missions that will be operational for decades, the probability of encountering at least one major magnetar flare is significant. Engineers are designing more robust electronics, better shielding, and automated protection systems that can respond in milliseconds. But there's only so much you can do. A truly giant flare, one comparable to the March 1979 event, would destroy most spacecraft regardless of shielding. The radiation intensity would simply be too high. Electronics would fry. Solar panels would degrade instantly. Even the spacecraft structure itself might suffer damage from the intense electromagnetic fields inducing currents through metal components. Future interstellar probes face even greater risks. As we send spacecraft toward nearby stars, they'll spend decades or centuries in deep space. The probability of a magnetar flare intersecting their path increases with time. We might lose probes to events we can't predict or prevent. It's a sobering thought. Our ambitions to explore the galaxy are constrained by the galaxy's own violence. Every magnetar will die. Not in the explosive sense, but in the slow decline of energy. The magnetic field will weaken, the rotation will slow, the surface will cool. Eventually, the object that once terrorized its corner of space will become quiet. But what happens then? Scientists have debated this for decades. The answer depends on mass. A magnetar's mass determines its ultimate fate, just as mass determined its birth. And the critical threshold is roughly 2 to 3 times the mass of our star. This is called the Tolman-Oppenheimer-Volkoff limit, the maximum mass a neutron star can support before gravity overwhelms neutron degeneracy pressure. Most magnetars are probably below this limit. They formed from stars massive enough to create neutron stars, but not so massive that the core exceeded the critical threshold. These magnetars will never become black holes. They'll simply fade. The magnetic field will decay over millions of years. The rotation will slow to once every several seconds or minutes. The surface will cool to near absolute zero. What remains is called a black dwarf, though that's a misleading term. It's not related to white dwarfs. It's simply a cold, dead neutron star. Still incredibly dense, still warping space-time, but emitting no detectable radiation. Just a dark sphere floating through space, invisible unless something passes close enough to feel its gravity. But some magnetars might be right at the edge. If a magnetar's mass is very close to the limit, it might be supported only by the outward pressure from its magnetic field and rotation. As these energy sources decline, the support weakens. Eventually, the magnetar could cross the threshold. In an instant, gravity would win. The neutron star would collapse into a black hole. This process wouldn't be dramatic from the outside. No explosion, no flash of light. The magnetar would simply vanish, replaced by a tiny black hole perhaps 20 miles across. Any magnetic field would disappear. The rotation would become irrelevant. The object would transform from one extreme state to another. We've never observed this transition. It might happen too quickly to catch. Or magnetars might lose enough mass through particle winds and radiation that they safely fall below the critical threshold before collapse becomes possible. We don't know. The theoretical models give different answers depending on assumptions about the equation of state, the relationship between pressure and density in ultra-dense matter. There's also the possibility of accretion-induced collapse. If a magnetar exists in a binary system, it might gain mass from a companion star. This additional mass could push it over the limit. The neutron star would collapse into a black hole while still relatively young and active. This scenario might explain some mysterious transient events astronomers have observed. Some researchers have proposed that we might detect these collapses through gravitational waves. As the magnetar contracts rapidly into a black hole, it would emit a brief burst of gravitational radiation. Detectors like LIGO and Virgo might pick up these signals if they occur in our cosmic neighborhood. So far, nothing definitive has been detected, but we're still in the early days of gravitational wave astronomy. The universe might contain billions of dead magnetars scattered throughout galaxies, invisible remnants of violent pasts, too cold to emit radiation, too small to notice unless you're right next to them. And mixed in with them might be small black holes, the final form of magnetars that cross the threshold. We'd have no way to tell them apart from a distance. But regardless of which path a magnetar takes, its reign of terror is temporary. 10,000 years of violence, then millions or billions of years of silence. The universe's most extreme objects are also among its most transient. They blaze brilliantly and briefly, then vanish into darkness, remembered only by the scars they left on space-time itself. Physics has limits. Not because our theories are incomplete, though they are, but because nature itself has boundaries. There are maximum temperatures, maximum densities, maximum field strengths, beyond which the laws we know break down completely. Magnetars push us right up against several of these limits. Start with magnetic field strength. In theory, magnetic fields can increase without bound, but practically, they can't. At around 10 to the 17 Gauss, the magnetic field becomes so strong that the energy density exceeds the mass energy density of matter itself. The field would curve space-time more than the object creating it. It becomes gravitationally self-interactive, generating its own gravity. This is called the quantum critical field strength. Magnetars reach fields of 10 to the 15 Gauss. That's only 1% of the quantum critical limit, but it's close enough that quantum effects become important. Virtual particles in the vacuum respond to the field. Photons split. The vacuum becomes polarized. We're in a regime where quantum mechanics and general relativity start overlapping, the regime where our theories struggle. Testing physics in these conditions is impossible in laboratories. Our strongest sustained magnetic fields reach maybe 50 Tesla, about 500,000 Gauss. We can generate higher fields in pulse bursts, but only for microseconds before the equipment destroys itself. To reach magnetar-level fields would require energies we simply don't have access to. Nature provides the laboratory we can't build. Then there's density. Neutron star cores reach densities of roughly 10 to the 18 kilograms per cubic meter. That's about 5 times nuclear density, the density of an atomic nucleus. At this point, neutrons are packed so tightly that they're touching. There's no space between them, and we don't fully understand what happens when you push even further. Different theoretical models give different predictions. Some say the matter remains neutrons, just compressed even more. Others say quarks deconfine, creating quark matter. Still, others propose exotic phases with names like color superconductivity or pion condensation. We have equations, but no data to confirm which equations are correct. Magnetars and neutron stars generally are testing these theories naturally. Gravitational time dilation near magnetars approaches limits too. Time runs 30% slower on the surface compared to distant space. That's not close to the extreme time dilation near a black hole's event horizon, but it's significant. It's enough to measure relativistic effects with precision. Any deviations from general relativity's predictions would show up in magnetar observations. Temperature is another frontier. When magnetars form, their surfaces briefly reach temperatures of 1 billion degrees or more. That's hotter than any star's core. At these temperatures, thermal photons have energies comparable to electron rest masses. Particle-antiparticle pairs pop into existence from thermal energy alone. The distinction between matter and radiation blurs. Rotation provides yet another limit. Young magnetars can spin at several hundred rotations per second. At these speeds, the equator is moving at significant fractions of light speed. Material at the surface experiences enormous centrifugal forces fighting against gravity. Spin much faster, and the magnetar would tear itself apart. We're seeing objects at the physical limit of how fast something can rotate without disintegrating. All of these limits converge in magnetars. Extreme magnetism, extreme density, extreme gravity, extreme temperature, extreme rotation. Nowhere else in the universe, except perhaps inside black holes where we can't observe, do so many extreme conditions exist simultaneously in one place. Magnetars are nature's extreme physics laboratories, and they're telling us something important. The universe can reach these limits and sustain them, at least temporarily. Our theories predict collapse, instability, breakdown, yet magnetars exist. They're stable, or stable enough. This means our understanding, while incomplete, is at least approximately correct. We're on the right track. But there are hints of new physics lurking in the data, small discrepancies, behaviors that don't quite match predictions. These hints might be measurement errors, or they might be the first cracks showing in our current theories, pointing towards something deeper. Every observation brings us closer to knowing which. Since 2016, astronomers have been tracking something peculiar, a repeating fast radio burst source, designated FRB 121+65-2, sending out radio pulses at irregular intervals from a distant galaxy. Unlike most fast radio bursts that fire once and disappear, this source keeps pulsing, sometimes dozens of times in an hour, then silence for days, then bursts again. The pattern is chaotic, but it's not random. Statistical analysis shows structure. The bursts cluster during certain periods. They avoid others. There's a roughly 16-day cycle buried in the data, though not every cycle produces bursts. Whatever creates these signals is operating on a schedule we don't fully understand. In 2020, researchers tracked the source to a star-forming region in a galaxy 500 million light-years away. The precision location revealed it was near a massive star or stellar remnant. The timing cycle matched what you'd expect from a binary system, two objects orbiting each other. And the best candidate for producing such intense radio bursts remained a magnetar. Here's how it might work. A magnetar orbits a more normal star, maybe a blue giant or supergiant. As they orbit, tidal forces stress the magnetar's crust. When the stars are closest, roughly every 16 days, the stress peaks. This triggers starquakes and magnetic flares. Some of these flares produce radio emission that beams toward Earth. We see them as fast radio bursts. But not every orbit produces visible bursts. The radio beams are narrow, like lighthouse beams. They only hit Earth if they happen to be pointed our way during the flare. Most flares produce beams pointed elsewhere. We miss them entirely. This explains the irregular pattern. The magnetar flares predictably, but we only see the ones that align correctly. Other repeating sources show different patterns. FRB 180+57 has a roughly 157-day cycle. It bursts for several days, then goes quiet for months, then bursts again. This longer cycle suggests a different type of system, perhaps a magnetar with a more distant companion or a more complex orbital arrangement. Some scientists remain skeptical. They argue that not all repeaters fit the magnetar model comfortably. The energy outputs are sometimes too high. The burst durations are sometimes too short. There might be multiple types of sources producing repeating fast radio bursts, and magnetars are just one possibility. Alternative theories include neutron star mergers that somehow don't fully merge, or black holes, accreting matter in bursts, or even more exotic options involving cosmic strings, though most physicists consider that unlikely. The debate continues because the data is still limited. We have dozens of repeating sources now, but that's not enough to draw definitive conclusions. What's clear is that repeating fast radio bursts are giving us unprecedented access to studying whatever produces them. Single bursts appear and vanish. We can't follow up, can't gather more data, but repeaters let us point multiple telescopes at the source and wait. When the next burst comes, we're ready. We can measure polarization, frequency structure, intensity variations, all in exquisite detail. These detailed observations are revealing complexity we didn't expect. Some bursts show frequency drifting, the radio frequency changing during the pulse. Others show multiple sub-pulses clustered together. The emission mechanisms must be intricate, involving complex magnetic field structures and particle acceleration processes. If magnetars are responsible, these observations constrain how magnetar magnetic fields are structured. The field can't be a simple dipole, north and south pole configuration. It must be twisted, braided, with multiple active regions that can produce independent radio beams. This matches theoretical predictions about how magnetar fields evolve over time. And here's the exciting part. We're finding more repeaters every month. As telescope sensitivity improves, fainter sources become visible. Each new repeater adds data points. Patterns emerge. And with enough patterns, we'll finally crack the code. We'll understand not just what creates these bursts, but why they repeat, what drives the cycles, and what it tells us about magnetar behavior. We've traveled across the extremes, from magnetic fields that bend light to densities that warp time itself, from starquakes that outshine galaxies to radio signals that cross cosmic voids. We've seen how magnetars form, how they rage, and how they might eventually die. But there's one truth underlying everything, one realization that changes how we see the universe. We are fragile, unimaginably fragile, and the universe doesn't care. A magnetar 50,000 light-years away can flood our planet with radiation, a flare we can't predict, can't prevent, and can't survive if it's strong enough. Our entire technological civilization, everything we've built, depends on stable conditions, stable radiation levels, stable magnetic fields, stable climate. One major magnetar flare aimed our way, and that stability evaporates. But here's what keeps scientists up at night. Magnetars are just one threat. The universe contains countless others. Black holes, gamma-ray bursts, supernova explosions, asteroid impacts, solar flares. We exist in a shooting gallery, and we've been lucky so far. Earth has had 4 billion years to develop complex life. In that time, no nearby magnetar has fired at us directly. No gamma-ray burst from a dying star has sterilized our surface. We've dodged every bullet. How much longer will our luck hold? Probability says it will hold for a long time. The galaxy is vast. Dangerous objects are relatively rare. The odds of a catastrophic event in any given year are vanishingly small, but over millions of years, those odds accumulate. Over billions of years, they become certainty. Someday, somewhere, Earth's luck will run out, unless we've already left. The ultimate lesson from Magnetars isn't about Magnetars at all. It's about the necessity of becoming a multiplanetary species. If humanity remains confined to one world, we're one cosmic accident away from extinction. A magnetar flare, an asteroid strike, anything could end us. But if we spread across multiple star systems, no single event can eliminate us. Magnetars teach us the universe operates at scales and energies beyond our imagination. Objects exist that can release more power in a second than civilizations use in millennia. Forces exist that make our strongest technology look like children's toys. And these objects, these forces, they're not rare exceptions. They're part of the standard cosmic landscape. Every time we observe a magnetar, every time we detect a fast radio burst, we're reminded of our place. We're small, we're temporary. We live in a universe that creates and destroys on timescales and scales that dwarf human experience. Stars explode, black holes collide, magnetic fields twist space itself into knots. And through it all, life clings to tiny rocky worlds, hoping the chaos passes them by. But here's the paradox. That same violent universe created us. The heavy elements in our bodies came from stellar explosions. The energy that powers life came from a star. The magnetic field protecting Earth came from a molten core, a small-scale version of magnetar physics. We're made from cosmic violence. We exist because of it. Magnetars are not anomalies. They're not glitches in reality. They're reality showing its full range. The universe can be gentle, allowing planets like Earth to orbit stable stars for billions of years. But it can also be catastrophically violent, creating objects that bend and break every rule we thought was unbreakable. And maybe that's okay. Maybe the universe needs both, the quiet regions where life can emerge and the violent regions that forge the elements life requires. The balance between creation and destruction, played out across cosmic time. We're here now, in this moment, on this planet, looking up at a sky filled with wonders and terrors. Magnetars pulse in the darkness, invisible to our eyes but blazing in X-rays. They remind us that the universe is larger, stranger, and more dangerous than we can fully comprehend. But they also remind us that we're capable of understanding. We've detected these objects, measured their properties, built theories that explain their behavior. We've taken the most extreme phenomena nature produces and turned them into science. That's remarkable. That says something about what human minds can achieve. So yes, magnetars are terrifying. They're objects of pure extremity, pushing every physical law to its breaking point. They can destroy worlds from light years away. They operate on energy scales that make stars look dim. They represent everything that makes space hostile to life. But they also represent everything that makes space beautiful. The universe, at its absolute limit, physics tested to destruction, and somehow, miraculously, holding together. Reality proving it's weirder, more violent, and more wonderful than any fiction we could invent. That's the truth about magnetars. They're not just cosmic monsters breaking every rule. They're proof that the rules themselves are more flexible, more extreme, and more incredible than we ever imagined. They're the universe, showing us what's possible when you squeeze matter, energy, and magnetic fields until something has to break. And nothing breaks. Everything transforms. Space isn't empty near a magnetar. It's crowded with invisible forces that reach out thousands of miles, grabbing anything that passes by. These forces don't just pull through gravity. They push, twist, and accelerate through pure magnetism. And if anything survives long enough to orbit a magnetar, that orbit becomes a nightmare of physics. Normal orbits follow simple rules. Gravity pulls inward, velocity carries you forward. The balance creates an ellipse. Planets orbit stars. Moons orbit planets. The math is clean, predictable. Newton figured it out 300 years ago. Einstein refined it. But near a magnetar, those clean equations collapse under the weight of extreme magnetism. Here's what happens. Take a hypothetical asteroid, somehow surviving in orbit around a magnetar at a distance of 1,000 miles. Gravity tries to hold it in a stable path, but the magnetic field interferes. If the asteroid contains any iron or nickel, and most asteroids do, the field tugs on it. Not uniformly, different parts of the asteroid experience different magnetic forces depending on their composition and orientation. This creates torque. The asteroid starts tumbling. Its rotation becomes chaotic, unpredictable. The tumbling changes how magnetic forces act on it. Sometimes the field accelerates it. Sometimes it breaks. The orbit destabilizes. Over days or weeks, the asteroid either spirals inward, crashing into the magnetar's surface, or gets flung outward, escaping into interstellar space. But that's assuming the asteroid stays solid. At 1,000 miles, the magnetic field strength still exceeds 1 billion Gauss. Any material with magnetic properties experiences massive internal stresses. Iron crystals align with the field, creating strain. If the asteroid has any structural weaknesses, any cracks, the magnetic stress rips it apart. The asteroid becomes a cloud of fragments, each following its own chaotic path. Scientists have modeled what a debris disk around a magnetar would look like. The answer is disturbing. Nothing stays in stable orbit. Material constantly falls inward or gets ejected. The disk would be ephemeral, constantly replenished by magnetar flares ejecting surface material, constantly depleted by magnetic forces clearing it away. Any observer would see a shimmering ring of doomed matter spiraling and fragmenting in real time. Could a planet survive near a magnetar? The answer is almost certainly no. Any planet close enough to be interesting would be tidally locked, one face always toward the magnetar. That face would receive constant bombardment from radiation and particle winds. The atmosphere, if there was one, would be stripped away in years. The magnetic field would induce enormous currents in the planet's core and crust, heating it from within until the surface melted. Even far away, maybe millions of miles out, where the field weakens and radiation becomes survivable, there's still a problem. Magnetars don't emit energy steadily. They flare unpredictably. A planet that survived for decades in a stable orbit could be flash-fried without warning when the magnetar erupts. Any ecosystem that somehow evolved would be sterilized repeatedly, reset to zero each time. But here's the truly strange part. Some neutron stars, possibly including dormant magnetars, do have planetary systems. We've detected them. Radio pulses from pulsars show timing variations caused by orbiting objects. These planets orbit at distances of millions of miles, far enough to avoid immediate destruction. They're not original planets from before the supernova. They formed afterward from the debris disk. This means planets can form around neutron stars, and if they can form around regular neutron stars, maybe they can form around magnetars during the dormant phase after the magnetic field has decayed. These worlds would be dark, frozen, bathed in X-rays instead of visible light, but they'd exist, silent witnesses to the violence that created them. And if planets can exist, what else might survive out there? August 26, 2008, astronomers detected a supernova in a nearby galaxy, NGC 641, about 13 million light-years away. They designated it SN 2008D. It appeared normal at first, a massive star exploding, brightening rapidly, then beginning its slow fade. Telescopes tracked it for weeks. Standard procedure. But this supernova didn't fade normally. After the initial decline, it brightened again. Then it stayed bright, far too bright for far too long. Something inside the expanding debris was pumping energy into it, making it glow like it had a hidden power source. Scientists scrambled to explain what they were seeing. The answer became clear through careful analysis of the light spectrum and energy output. A magnetar had formed in the explosion. Not just any magnetar, but one of the fastest spinning, most energetic objects ever detected. It was rotating roughly 1,000 times per second, so fast that its equator was moving at 20% of light speed. This magnetar was newborn, perhaps hours old when we first saw it. As it spun, its massive magnetic field acted like a brake, slowing it down through magnetic dipole radiation. The rotational energy, enormous quantities of it, converted into electromagnetic radiation. This radiation heated the surrounding supernova debris from the inside, making the whole thing glow far brighter than it should. Scientists calculated the numbers and they were staggering. The magnetar was releasing more energy in a single day than our star releases in 100,000 years, all of it coming from spin down. The object was literally spinning itself to death, bleeding rotational energy into space through its magnetic field, and we were watching it happen in real time. This discovery confirmed theories about magnetar birth. We'd suspected young magnetars spun incredibly fast, but we'd never caught one fresh from formation. SN 2008D gave us a front row seat. Every observation revealed new details. The spin down rate told us the magnetic field strength. The brightness told us the energy output. The spectrum told us what the surrounding material was made of. Over the following years, astronomers continued watching. The supernova remnant gradually faded as the magnetar slowed. The spin period increased from 1 millisecond to several milliseconds. The energy output dropped, but even as it slowed, the magnetar remained incredibly powerful, still outshining thousands of normal stars. Then, roughly 3 years after formation, something changed. The magnetar had its first detected flare, a brief spike in X-ray emission captured by multiple satellites. This was expected. Young magnetars are unstable. Their crusts are still forming, still settling. Starquakes should occur frequently in the first few years. This flare confirmed the object was indeed a magnetar and not some other exotic possibility. But here's what made this observation revolutionary. We'd never tracked a magnetar from birth before. Every other magnetar we knew had already existed for years, decades, or centuries when we found them. We were seeing their middle age or later. SN 2008D gave us the complete life cycle from the very beginning. The data revealed that magnetars don't start at full strength. The magnetic field builds up over time as the interior settles and currents align. The very youngest magnetars might have fields weaker than their peak values. They strengthen during the first years, reaching maximum intensity, then begin the long decay. It's like watching a star form, but compressed into a time frame we can actually observe. This young magnetar also answered questions about supernova diversity. Astronomers had been puzzled by certain bright supernovas that didn't fit standard models. Now we knew. Some were magnetar-powered. The newborn magnetar acts like a cosmic battery, storing rotational energy and releasing it as radiation. This extra energy makes the supernova appear superluminous, hundreds of times brighter than normal. We've since found more examples. Supernovas that stay bright too long, that show the telltale signs of a central engine pumping energy outward. Each one teaches us something new about how magnetars form and evolve in their critical first months. But we've also learned something sobering. We can only observe this process if the supernova happens relatively nearby, within a few 100 million light-years. Further away, the details blur. We might miss the magnetar signature entirely. This means there could be hundreds or thousands of young magnetars forming every year across the universe, and we're only seeing the nearest ones. Each birth is a cosmic drama. A massive star dies, its core collapses, and for a brief moment, rotating 1,000 times per second, a magnetar blazes to life. August 17, 2017. Gravitational wave detectors sensed something extraordinary. Two neutron stars, locked in a death spiral for billions of years, finally collided. The merger happened in a galaxy 130 million light-years away. Telescopes across Earth swiveled to observe. What they saw changed astronomy forever. The collision produced gravitational waves that rippled through space-time. It created a kilonova, an explosion powered by radioactive decay of heavy elements. It sent out gamma rays, X-rays, radio waves, every type of radiation we can detect. The observations confirmed decades of theory about what happens when neutron stars merge. But here's the question that haunts scientists. What if one of those neutron stars was a magnetar? What if, instead of two ordinary neutron stars meeting, a magnetar collided with a companion? Nobody has observed this yet, but the theoretical predictions are nightmarish. Start with the approach. Two neutron stars spiraling together emit gravitational waves. The waves carry away orbital energy, causing the objects to fall closer. This is standard physics, confirmed by observation. But a magnetar adds complications. Its magnetic field extends thousands of miles. As the companion neutron star enters this field, it experiences enormous magnetic forces. If the companion has its own magnetic field, and all neutron stars do, the two fields interact. They can attract or repel, depending on alignment. The orbit becomes unstable. Instead of a smooth spiral, the neutron stars might experience sudden accelerations or decelerations as their magnetic fields lock and unlock. The gravitational wave signal would show irregularities, stutters in the frequency sweep. The magnetic interaction heats both objects. Currents induced in their crusts from passing through each other's fields generate thermal energy. The surfaces glow brighter. Material might even be ejected before the actual collision, blown off by magnetic pressure. This pre-merger emission would be a unique signature, telling observers that at least one object is a magnetar. Then comes the collision itself. The impact lasts milliseconds. Two spheres of ultra-dense matter, each 12 miles across, slam together at significant fractions of light speed. The energy release is inconceivable, temperatures reach trillions of degrees, magnetic fields compress, reaching strengths that should be impossible even for magnetars. In those milliseconds, several things can happen. If the combined mass is below the maximum for neutron stars, roughly 2.4 to 3 times the mass of our star, depending on the equation of state, the merged object might survive as a hypermassive neutron star. It would be unstable, spinning incredibly fast, but it wouldn't immediately collapse. This hypermassive remnant would have a magnetic field created by merging two fields. If one was a magnetar field, the result could be a field even stronger than either original. For seconds or minutes, the universe would contain the strongest magnetic field ever created, powerful enough to affect space-time geometry directly. But this can't last. The hypermassive neutron star is supported only by rapid rotation. As it radiates gravitational waves and electromagnetic energy, it slows down. Centrifugal support decreases. Gravity wins. The object collapses into a black hole. The collapse happens fast. In less than a second, 12 miles of magnetar becomes a singularity surrounded by an event horizon. The magnetic field doesn't disappear instantly. It's frozen into the remaining material outside the event horizon, the accretion disk of debris. This magnetized disk can power jets, beams of particles, and radiation shooting out along the rotation axis. These jets might explain some gamma-ray bursts. The short-duration bursts, lasting under 2 seconds, come from neutron star mergers, but some are brighter than others. Some show features in their spectra that standard merger models don't predict. If one neutron star was a magnetar, the extreme magnetic field could explain these outliers. The material ejected during the merger carries magnetic field with it. This magnetized ejector behaves differently from normal merger ejector. The field confines the material, channels it, creates structure. The kilonova that follows might be asymmetric, brighter in some directions than others. Observers at different angles would see different brightnesses and colors. We haven't definitively observed a magnetar neutron star merger yet. The statistics say they should be rare. Magnetars are active for only 10,000 years. The probability of catching one during a merger in that narrow window is low, but the universe is vast. Somewhere, sometime, it happens. And when we finally detect one, when gravitational wave detectors alert us and telescopes capture the light show, we'll witness something unprecedented. The merger of extreme and more extreme. The collision that creates, for a brief instant, the most powerful magnetic field the universe can produce. In the desert of South Africa, a forest of antennas points skyward. This is Meerkat, one of the most sensitive radio telescope arrays ever built. 64 dishes working together, combining their signals to see things no single telescope could detect. And among its many targets, it's hunting for something specific. The quiet whispers between magnetar flares. Most magnetar observations focus on the dramatic, the giant flares, the X-ray bursts, the events that light up detectors across the electromagnetic spectrum. But between these outbursts, magnetars aren't silent. They emit steady radio waves, weak but detectable if you know where to look and how to listen. These radio emissions are different from flare-associated bursts. They're persistent, always there, pulsing at the magnetar's rotation period. Scientists call them quiescent radio emission. The term is misleading because there's nothing quiet about a magnetar, but compared to a giant flare, this emission is a whisper. Meerkat excels at detecting whispers. Its dishes are spread across 5 miles of South African terrain. When they work together, they create a virtual telescope with incredible sensitivity and resolution. It can detect radio signals thousands of times weaker than previous telescopes could manage, and it's using this capability to systematically survey known magnetars. The results are surprising. Some magnetars that were thought to be radio quiet actually emit faint but steady radio pulses. Others show variability. their radio brightness changing over days or weeks with no corresponding X-ray activity. A few exhibit polarization patterns that reveal the structure of their magnetic fields in unprecedented detail. But Meerkat has found something even more intriguing: microflares, tiny bursts of radio emission lasting milliseconds, occurring randomly between major flares. Each microflare releases only a tiny fraction of the energy of a giant flare, but they happen frequently, sometimes dozens per day, and they're telling scientists something crucial about Magnetar magnetospheres. The magnetosphere is the region around a magnetar where the magnetic field dominates. Charged particles get trapped, spiraling along field lines. The magnetosphere extends hundreds of miles from the surface, invisible but constantly active. And these microflares appear to be caused by small-scale magnetic reconnection events in this region. Think of it like lightning. A thunderstorm builds up charge separation. Eventually, the electric field becomes strong enough to ionize air, creating a lightning bolt. Magnetar magnetospheres work similarly. Magnetic stresses build up, field lines twist. Eventually, a small region becomes unstable and reconnects, releasing a burst of energy as a microflare. By studying thousands of these microflares, scientists are mapping Magnetar magnetospheres in detail. Each flare tells them about field strength, field geometry, and plasma density at the location where it occurred. It's like doing tomography, building a three-dimensional picture from many individual data points. This work is revealing that Magnetar magnetic fields are far more complex than early models suggested. They're not simple dipoles with north and south poles. They're twisted, knotted, with multiple active regions. Some areas are relatively stable, others are constantly reconnecting. The field is dynamic, evolving on timescales of days to weeks. Meerkat is also searching for something that theory predicts but hasn't been confirmed: magnetar precession. If a magnetar's magnetic axis doesn't align with its rotation axis, the object should wobble like a spinning top. This wobble would show up in the radio data as periodic variations in pulse arrival times and intensity. Finding precession would be revolutionary. It would tell us about the magnetar's internal structure, how mass is distributed inside. It might reveal whether the core is superfluid, whether the magnetic field penetrates all the way through, whether there are currents flowing between the crust and core. All of this from watching the radio signal carefully over months or years. But there's a deeper goal driving this research. Scientists want to understand how magnetars eventually turn off. What happens in the final years before they go dormant? Does the radio emission suddenly cease, or does it fade gradually? Do the microflares become less frequent, or do they continue until the very end? Answering these questions requires long-term monitoring. Meerkat can do this. It can observe the same magnetars month after month, year after year, building up a timeline of their decline. And with next-generation telescopes coming online, like the Square Kilometre Array, which will be 50 times more sensitive, we'll be able to track even the faintest whispers. The goal is to catch a magnetar in the act of dying, to observe the transition from active to dormant in real time. Nobody has done this yet, but with telescopes like Meerkat watching, we might finally witness the end of a magnetar's violent reign. There's a scenario that keeps astronomers awake. Not probable, but possible. Not likely, but not impossible. A discovery that would force us to rethink everything we know about magnetars and maybe about physics itself. And some scientists think we might be close to finding it. Imagine this: a radio telescope detects a signal, not random noise, not a glitch, a pattern, repeating at precise intervals. The pattern is complex, too complex to be natural. It shows structure, organization, information, and it's coming from a magnetar. The immediate reaction would be skepticism. Instruments malfunction, interference happens. Patterns appear in noise that aren't really there. The human brain is wired to find patterns even in randomness. Every researcher would assume it's an error. They'd check and recheck, run the analysis again. Different telescopes would observe the same target, and if they all saw the same thing, if the pattern persisted, then the questions would begin. Could magnetars create organized signals naturally? The answer, according to current physics, is probably not. Magnetar emissions are driven by magnetic field dynamics, plasma physics, particle acceleration. These processes create pulses, bursts, even periodic variations. But complex patterns with information content? That requires something different. That requires organization at a level nature doesn't normally achieve. Unless we're wrong about what's possible, unless magnetar physics, pushed to absolute extremes, can create structures and phenomena that look artificial but aren't. Maybe the magnetic field configurations can form resonant cavities that amplify specific frequencies. Maybe plasma instabilities can organize into patterns that repeat with eerie precision. Maybe we're about to discover a new regime of physics where complexity emerges spontaneously from chaos. Or maybe, just maybe, someone is using magnetars, not creating them. We can't create magnetars, but using them, harnessing their energy, modulating their emissions, turning a natural cosmic object into a transmitter powerful enough to send signals across the galaxy. The energy requirements for interstellar communication are enormous. You need a transmitter powerful enough that the signal remains detectable across thousands of light years. Our most powerful radio transmitters can barely reach nearby stars before the signal becomes indistinguishable from noise. But a magnetar emits more energy in seconds than our civilization has produced in all of human history. If you could tap even a fraction of that, modulate it somehow, you'd have the ultimate transmitter. Science fiction has explored this idea. Authors have written about advanced civilizations using stars as beacons, but magnetars make more sense for this purpose. They're brighter in the right wavelengths. Their emissions are already pulsed, making them easier to modulate, and they're rare enough that finding one and claiming it might be feasible for a sufficiently advanced civilization. No credible scientist thinks we've found such a signal yet. The fast radio bursts and repeating sources all appear to be natural phenomena. The patterns we see are consistent with magnetar physics. There's no need to invoke intelligence, but the possibility exists, and as our telescopes become more sensitive, as we study more magnetars in greater detail, we might find something anomalous. What would we do if we did? The protocols are unclear. Science has procedures for confirming discoveries. You replicate, you peer review, you rule out alternative explanations. But what if the alternative explanations run out? What if every natural process is exhausted and the signal remains unexplained? The implications would be staggering. It would mean we're not alone. It would mean intelligence exists at a level capable of manipulating neutron stars. It would mean the universe contains civilizations so far beyond us that we're like ants trying to comprehend nuclear physics. And it would mean they're out there, possibly watching, possibly waiting. But there's another possibility that's equally unsettling. What if we find evidence of magnetar engineering that's old? What if we detect patterns in magnetar emissions that are clearly artificial but haven't changed in millions of years? That would mean the civilization that created them is gone, dead, extinct, leaving behind only their monuments in the form of modulated stellar corpses. That scenario carries its own warning. If a civilization advanced enough to harness magnetars can go extinct, what chance do we have? What killed them? Was it war? Environmental collapse? A cosmic disaster they couldn't prevent despite all their technology? Or did they transcend, upload themselves into virtual realities, leave the physical universe behind? We'd be staring at an answer we can't interpret. These are the thoughts that drive some researchers to keep searching, not because they expect to find anything. The universe is vast. The odds are astronomical, but because not searching seems worse. Because if there's even a 1 in a million chance that magnetars are being used, that intelligence has touched these objects. We need to know. And so the telescopes watch Meerkat in South Africa, FAST in China, the Very Large Array in New Mexico, dozens of others, all gathering data, all analyzing signals from magnetars and other neutron stars, looking for patterns, looking for anomalies, looking for anything that doesn't fit. Most likely, they'll find nothing. Magnetars will remain what we think they are: natural objects, extreme but comprehensible, the universe showing off its raw power without purpose or meaning. But the search continues, because the day we stop looking is the day we accept that we're alone, that intelligence is rare and brief, that the universe is just physics playing out across time and space with no one to witness it except us. And maybe we're not ready to accept that yet.